surface. All right, so this is actually the function define a lower surface. Remember, now we're in a three-dimensional space. So we don't have a lower curve anymore. We have a lower surface. And also this is the upper surface. Okay, so if I'm looking at this intergradient region, which is in the first quadrant and pressed by this plane, so xy is actually coming from this triangle. All right? Are you with me? xy is actually coming from this triangle. So if we identify it as a z-simple region, this triangle lining on the xy plane is indeed my R here. I want every one of you to agree with me how to identify R on the xy plane. Okay? So you can convince yourself in two equivalent ways. One way you can convince yourself is that this intergradient region in a three-dimensional space is indeed built upon this triangle on the xy plane. Am I right? Yeah. Is it? Yeah. Am I right? The other thing is, if you can imagine, we can squeeze the whole three-dimensional space intergradient solid onto xy plane. If you squeeze everything back to the xy plane, you're going to get this right angle. Am I right? Or, mathematically speaking, if you project everything back onto the xy plane, you're going to get this right angle, which is exactly R here. Am I right? Which is exactly R here. So, in order to identify this intergradient region, this is what I have to do. So, this right triangle, this right triangle lining on the xy plane is the region R here. And then, in order to identify my triple integral, I want to have my two functions first. Okay, I want to have my two functions to define the lower curve and the upper curve. The lower surface and upper surface now. So I'm looking for the equation to define the lower surface. What is the lower surface for this intergradient region?
Triangle.
It is exactly defined by the plane on the xy plane, all right? So z cannot be even lower than the xy plane. Are you with me? So the lower surface I'm looking at is actually the xy plane. And I'm looking for equation to define the xy plane. What is the equation? Z equals 0. All right? So z is equal to 0. So this is indeed the lower surface, or the function to define the lower surface here. You agree with me? All right? This has to be the equation to define the lower surface, because this whole thing is intergradient solid. This solid is above xy plane, and the lowest is actually on the xy plane. So this is indeed the equation to define the lower surface. Now, what is the upper surface? What is the upper surface?
The entire the solid.
So this upper surface is talking about your z value cannot exceed that plane. All right? Cannot exceed that surface. But that surface is exactly the surface defined by this equation. All right? So your z value cannot be lower than the xy plane, cannot go beyond the plane defined by this equation. So this equation is actually going to define your upper surface. All right? Because I need two functions to define for z. So the lower function is z equals 0. I need to rewrite this equation as z is equal to a function of xy. And that function is going to be the equation to define the upper surface. Am I right?
Yeah.
Okay? So this is going to be our goal. So I want to rewrite this equation. So z is equal to 5z is equal to minus 5x minus 25y plus 25. So z is going to be equal to minus x minus 5y plus 5. Okay? So if we're interpreting a constant function 1, this is the 1. So in order to identify this as a z-simple region, you need a region on the xy plane where this whole region in the three-dimensional space is built upon. Okay? You need an R on the xy plane. And then you need a lower function and upper function that define these two surfaces. Now with me? As long as we fix z, everything will be reduced to a double integral. If I fix z about this R, I need to identify this R as a region involving x and y. which is essentially identifying a region for a double integral. And we have done that so many different times. All right? So if I want to identify this region lying on xy plane as a y-simple region, because I'm writing y in the interior, I need two numbers for x and two functions for y. Are you with me? So I need two numbers for x and two functions for y. So the two numbers for x is going to be 0 and 5. So essentially, this is going to be from 0 to 5, and I can need two functions for y. So essentially, I needed to see y is bounded below by a function and above by a function. Y cannot go as small as 0. All right? So y is bounded by 0. Or you can simply understand this is in the first option. Y has to be bounded by 0. So y is bounded by 0 up to a function which is defined by this trace. All right? So y can go as low as 0 and as large as the point lying on the trace right here. All right? Essentially, I need two functions. One function is y equals 0. The other function is coming from the function of this guy. All right? So essentially, it's coming from a function defining the trace. And I need a y is equal to a function of x. So I need to solve for y in this trace equation. All right? So essentially, I'm going to get a y is equal to minus 5x plus 5. And then z is from 0 to minus x.
1/5.
1/5.
1
Oh, I'm
minus.
sorry. So 25y is equal to, yeah, so it should be 5 divided by x.
1 minus 1.
And then plus
X
1.
over.
All right? Plus 1. And then z is from 0 to minus x minus 5y plus 5. Then my intervening function is still 1 dz dy dx. Okay? So it is exactly coming back this example, right? So I can identify that intervening region in a three-dimensional space as a y-simple region in 3D, y-simple region in 2D. Are you with me? So I'm going to keep using this terminology. It's a z-simple region, which means I need a lower surface and upper surface. I need a region in xy plane. And then back onto the xy plane, I can identify it as a y-simple region. So I need two numbers for x and two functions for y. Are you with me? Okay, now I want to begin our whole game today. So not only I can identify my region R as a y-simple region, I can also identify it as a x-simple region also. All right? This thing is just a right angle lining on the xy plane. So this is pretty much the easiest object we dealt with on double integrals. So not only I can identify it as a y-simple region, I can also identify it as a x-simple region. Which means after I have this R on xy plane, and z is going from 0 to minus x minus 5y plus 5 dz. Not only I can write it as dy dx, I can also write it as dx dy. Okay? So this is a z simple in space, x simple on the plane. Okay? So let's do it. If it is a x simple region, I need two numbers for y and two functions for x. So the two numbers for y are 0 and 1. X is bounded by 0 and a function coming from this trace equation again. All right, so x can go from 0 up to a point lying on this straight line. Okay, so it's going to be from 0 to 1 for y, and I need to solve for x in this equation. So solving for x in this equation is going to be minus 5y plus 5. 0. So from 0 to minus x minus 5y plus 5, 1 dz dx dy. Okay? So we can identify the same intervening region as z simple in a space, y simple on a plane, as well as y simple on the as well as x simple on the plane. Okay. Agree? Now.
How did you choose the upper bound?
Oh, this one, right?
Yeah.
So this one is still coming from the space equation. All right. So instead of solving for y for the y simple region, I need to solve for x for the x simple region because I need a function for x. So solving for x, I'm getting 5x is equal to minus 25y plus 25, and dividing both sides by 5. That's where I get that equation over there. You with me? Okay. I got an upper function for y. Okay. Now I have two remarks to make. First remark. I'm taking the integral with respect to constant function 1, not by coincidence. I actually want to convince you something. So in a double integral case, if I want to compute the volume of this solid, what did we do? If we compute the volume of this solid, what did we do? We take the integral of the difference between the upper surface and the lower surface upon this region, all right? So this is basically a solid in a three-dimensional space. And in double integral, we can compute the sign volume. And in this case, the sign volume has to be positive volume. And it is the double integral on this region R of the difference between these two surfaces, all right? So the upper surface is defined by this equation, and the lower surface is nothing but the xy plane. And we actually saw that right in here. All right? I actually saw it right in here because I am taking the double integral on the region on the xy plane and difference between the upper function and the lower function. So this is indeed the volume of this solid. All right? So when I'm computing this triple integral of a constant function 1, I can easily reduce it to a double integral as the integral of a difference between these two functions upon a region. So I am actually computing the volume of the solid. So this guy is nothing but the volume of the solid. Okay, this is nothing but the volume of the solid. And indeed, we can generalize our formula a bit. For any region, any solid region in R3, so any solid region in R3, computing the double integral, computing the triple integral of a constant function 1 in this region is going to give you the volume of this region. Okay? So if you have a solid region in R3 and you want to compute its volume, the only thing you need to do is to compute the triple integral with respect to a constant function 1. And this should be compared with the formula we learned before, the area formula in R2. Do you still remember that? Right? So if R is a region in R2, so we compute the area of this region by taking the double integral of a constant function 1, right? So these two formulas are pretty nice formulas as the applications of our multivariable integrals. If you have a region in R2, no matter how irregular it is, we actually apply this formula to compute the area of a disk, all right, which is pretty powerful for calculus. We can also compute any solid region in R3 by taking a triple integral. So this very nice application of triple integral is to find the volume of some solid region in R3. So I will give you one application to compute the volume of a ball. Okay, I will give you the application of using triple integral to compute the volume of a ball. But before we go there, I'm looking at this Z simple region identification of this solid over there. Instead of identifying this region as a Z simple region, in fact, I can also go X simple in the space. I can also go Y simple in the space. I'll explain what I mean. So if I want to go for X simple in a space, I need a function which is to the positive direction of axis and negative direction of axis. which is basically bounding this region in the x direction, right? So in the z direction, we have a lower and upper surface. In the x direction, you also have a lower and upper function, only in the z direction. Can you imagine that? Okay, so if I'm looking at this region in the three-dimensional space in the x direction, this is bounded by the surface lying on the yz plane. All right? Are you with me? This is bounded by the yz plane right here, and bounded by the plane defined by this equation. So in the z direction, you cannot go as small as 0, which is bounded by yz plane, and as large as the points lying on this plane. All right? So having this three-dimensional imagination here. So if I'm looking at this same region, solid region, in the x direction, I can go as beyond as the plane defined by this equation, as small as the plane lying on yz plane. Are you with me? Okay. So similarly, I can also go on the y direction, and this solid will be bounded by xz plane as the lower surface, and the surface defined by this equation as the upper surface. All right? So we can indeed use the exact same idea to identify this solid region as x simple and y simple as well. Okay? Now I want to quickly give you how we can do that. So now, remember when we discussed on Monday's class, we have 3 independent variables, right? So this triple integral, we can write down the triple integral in how many different combinations? 6. We can write it down in 6. We have achieved 1, 2 different cases, right? So we have achieved 1, 2 different cases. We can write down it into, say, dx, dy. So let's quickly practice that. In order to do that, first of all, I need a lower function for x and an upper function for x. And then I need to squeeze everything in the solid back onto yz plane to get a region on yz plane. All right? So this is pretty much the same principle as we did for the z simple region. Only difference is, in that case, we're squeezing everything down to xy plane. Here we have to squeeze everything down to yz plane. So in the x direction, I'm going to squeeze everything back onto the yz plane. So